A new chapter in humanity's search for life beyond Earth is unfolding quietly, not through imagination or speculation, but through the patient decoding of ancient light that has crossed unimaginable distances to reach us. For centuries, the night sky inspired one persistent question. Among the countless stars scattered across the darkness, are there worlds like our own? And if such worlds exist, could they harbor life? For most of human history, this question belonged to philosophy and wonder. It lived in poetry, belief, and curiosity. Today, it has become something far more tangible. It is measurable, testable, and deeply scientific. This transformation did not happen overnight. It emerged from decades of technological progress. Each generation built instruments more precise than the last, pushing the limits of what humanity could observe. Now, that boundary has moved farther than ever before. A new class of observatories has transformed how we study the cosmos. These instruments do more than capture images of distant stars and galaxies. They analyze light itself. Every beam of starlight carries hidden information encoded within its spectrum, revealing the environments it has traveled through. By breaking light into its component wavelengths, scientists can uncover chemical signatures left behind by the atmospheres of distant planets. These faint fingerprints allow researchers to identify gases that exist hundreds of light-years away. Instead of simply detecting planets, we can now begin to study them. Temperature, atmospheric composition, and even chemical imbalances can now be inferred across vast distances of empty space. Humanity has effectively developed a form of remote sensing on a cosmic scale, allowing us to investigate worlds we may never physically reach. Recently, one particular planet has drawn significant attention from researchers. Orbiting a faint star more than 100 light-years away, this world belongs to a class known as sub-Neptunes. These planets are larger than Earth but smaller than gas giants, occupying a strange middle ground that does not exist in our own solar system. For a long time, sub-Neptunes were considered unlikely candidates for life. Their thick atmospheres and extreme pressures seemed far too hostile. But that assumption is beginning to change. This planet's orbit places it within the habitable zone, the region around a star where temperatures could allow liquid water to exist under the right conditions. This does not confirm habitability, but it makes the planet scientifically compelling. The real breakthrough came through transit spectroscopy. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching our telescopes. During this brief moment, the atmosphere leaves faint chemical imprints on the light. These imprints can be analyzed to identify specific molecules. In this case, scientists detected water vapor, carbon dioxide, and methane. None of these gases alone prove the presence of life. But together, they create a chemical environment that invites deeper investigation. Then came something even more intriguing. Researchers found tentative hints of a molecule rarely associated with non-biological processes. On Earth, it is strongly linked to living organisms, especially microscopic marine life. Its presence elsewhere does not confirm biology, but it raises a possibility that cannot be ignored. Either unknown chemistry is at work, or something more complex may be unfolding. Scientific caution remains essential. Observations like these must be repeated, verified, and tested against every possible alternative explanation. The history of science is filled with signals that initially appeared extraordinary but later found natural explanations. Yet even within this caution, something has changed. We are no longer asking whether we can detect life. We are beginning to ask how to recognize it. If life exists on such a world, it would almost certainly be unlike anything we know. This is not a second Earth. Its gravity is stronger, its atmosphere denser, and its surface conditions likely far more extreme. Beneath thick cloud layers, there may exist vast global oceans extending deep below the atmosphere under immense pressure. Sunlight may never penetrate these depths. Life there would not rely on light. Instead, it might depend on chemical energy, similar to organisms found in the deepest parts of Earth's oceans. On our own planet, life thrives in places once thought impossible. Microorganisms survive in hydrothermal vents where temperatures soar. They exist beneath Antarctic ice and in environments without oxygen or sunlight. These extremophiles demonstrate that life is not limited to gentle conditions. It adapts, evolves, and persists wherever chemistry and energy allow. This realization has expanded the boundaries of habitability. Worlds once dismissed as too extreme are now considered viable environments for life. Thick atmospheres, subsurface oceans, and unusual chemical environments are no longer disqualifying features. They are targets of investigation. The distant sub-Neptune fits into this new perspective. Its atmosphere could act as a stabilizing blanket, trapping heat and maintaining conditions below. If an ocean exists beneath, it could provide a vast environment for chemical interactions. Over immense periods of time, such interactions could lead to the emergence of simple life forms. Even microscopic organisms could leave detectable traces. Subtle imbalances in atmospheric chemistry may serve as indirect evidence. Combinations of gases that are difficult to explain through physics alone could become clues.